The Monty Hall problem. The so-called Monty Hall problem refers to a well-known American television game show that became very popular several decades ago. It was hosted by a person named Monty Hall, who would give participants the chance to win attractive prizes or end up with undesirable items. Although the format appeared straightforward, it turned out to contain one of the most intriguing mathematical and logical paradoxes when analyzing its actual probabilities. Despite seeming like a trivial game, it has caused intense debate, astonishment, and even confusion among all kinds of audiences, including people with advanced mathematical knowledge. To describe the situation in detail, imagine there are 3 closed doors on stage. Behind one of them lies a valuable prize, such as a luxury car, and behind the other 2, items that nobody would really want, like goats or something equally unappealing. The contestant initially chooses one of the 3 doors, for instance, door number 1. Up to that point, everything seems normal, but the interesting part comes next. The host, who knows exactly which door hides the prize, proceeds to open a different door from the one the contestant picked, and that he knows does not have the prize. Let us say the host opens door number 3, showing an undesirable item like a goat. This leaves 2 doors still closed, the one the contestant chose in the beginning, door number 1, and the other door that remains closed, door number 2. At this moment, the host poses the crucial question: do you want to stick with your original choice, door number 1, or switch to the other remaining door, door number 2? At first glance, most people reason that now that one door with a goat has been revealed, there are only 2 unopened doors, and they assume the chance of winning the car behind the originally chosen door, or the new door, is the same, meaning they believe it is a 50% chance for each. That is what intuition suggests, as it seems that once one door is shown to be wrong, the odds should be evenly split between the 2 remaining doors. However, mathematical analysis reveals something surprising. Switching doors significantly increases the chance of winning the car. More specifically, if you keep your original choice, the probability of winning remains close to 1/3, whereas if you switch, it rises to about 2/3. Put differently, if you always switch after the host reveals a goat, you can win roughly 2 out of every 3 times, while if you stay with your first choice, you will only win 1 out of every 3 times. This result clashes with the feeling that it must be a 50-50 situation, and has been the source of countless discussions. To deeply understand why this is so, it helps to break down the possibilities. Let us label the 3 doors as door number 1, door number 2, and door number 3. The contestant randomly picks one, for instance, door number 1. From the start, the chance that door number 1 has the car is 1/3, and the chance that it has a goat is 2/3. If by chance you initially chose the door that contains the car, which happens 1 out of every 3 times, then the host can open either of the other 2 doors, since both would hide goats. If you switch in that scenario, you end up choosing a goat, so you lose. If you keep your original door, you succeed. On the other hand, if you started with a door that has a goat, which happens 2 out of every 3 times, the host will open the one door among the 2 you did not pick that also has a goat, and therefore the remaining door will have the car. In that situation, switching guarantees you the prize. Summarizing, initially you have a 1 out of 3 chance of being correct, and a 2 out of 3 chance of having picked a goat. That means that as soon as the host deliberately reveals a goat, your best option is to switch to the other door. One of the most striking aspects of the Monty Hall problem is the deep contradiction between the mathematical reality and the intuitive perception of the contestant or the viewer. When it became widely known, it sparked a great deal of debate, with many people arguing that it could not possibly be better to switch doors. Even some academics and public figures defended the notion that switching offered no advantage. However, once you consider all possible scenarios, the mathematics is clear. The host's action is not random, and his knowledge of the prize's location creates an information asymmetry that changes the odds dramatically in favor of switching. This puzzle is an excellent reminder of how the human mind often stumbles when assessing conditional probability, meaning our tendency to misjudge the situation once an intermediate event reveals new information. We find it difficult to notice how the host's choice of which door to open and the knowledge behind that choice reshapes the scenario. Because of this, the Monty Hall problem has been extrapolated to contexts beyond its simple television show format, finding relevance in areas such as investment strategy and personnel policy, where we often face decisions that must be re-evaluated after receiving partial information from someone with greater knowledge than we have. In the world of finance, for example, one might have invested in a particular instrument. Suddenly, a hint arrives from someone better informed, ruling out a certain option as undesirable. The investor might erroneously think that this new information changes nothing. But if you draw parallels with Monty Hall, you may see how the act of discarding one alternative is based on privileged knowledge, which alters the probabilities in favor of switching rather than holding on to the original choice. We also often observe that people are psychologically reluctant to switch away from an initial choice. Some call this a status quo bias or an attachment bias. Monty Hall demonstrates that overcoming that resistance, which is based on a fear of making a worse choice, is actually advantageous in many scenarios. Re-evaluating the situation based on newly revealed information can be the best move, even if our instincts might say otherwise. Culturally, the Monty Hall problem stems from the game show Let's Make a Deal, and later captured the interest of statisticians and theorists under the official name. There was even a controversy when a columnist named Marilyn Vos Savant addressed the puzzle in a magazine, with many readers, including math professors, sending letters disagreeing with her explanation. Ultimately, most acknowledged their error upon doing more extensive demonstrations and seeing that switching indeed doubles the likelihood of winning the grand prize compared to not switching. To wrap up the discussion of this puzzle, one might say that the Monty Hall problem offers a compelling illustration of how our intuition can conflict with actual probability analysis. It shows us that once a person possessing superior information eliminates an option, the probabilities are not the same as they appeared at the start. By understanding this, we better appreciate how new data from a knowledgeable source can fundamentally alter a choice we thought was locked in. The paradox lies in that seemingly simple, yet surprisingly counterintuitive, mathematical truth. That in a scenario involving 3 doors, a host who knows where the prize is, and an option to switch after revealing a goat, the best strategy is the one that, for many of us, initially feels illogical. Hence, the Monty Hall problem stands as a timeless testament to the intriguing gap between what we assume about chance and what rigorous analysis proves to be true. The Banach-Tarski Paradox. The so-called Banach-Tarski Paradox is one of the most astonishing and impactful examples in set theory and geometry, as it describes a situation that seems to contradict every intuitive notion of volume and the conservation of matter. Formulated by mathematicians Stefan Banach and Alfred Tarski in the early 20th century, it demonstrates that what appears to be a solid, indivisible sphere can be decomposed into a finite number of pieces which, after specific movements and reassemblies, produce 2 spheres of the same size as the original. For someone hearing this for the first time, the idea sounds utterly impossible. How can an object duplicate itself out of thin air without adding any additional substance? However, this paradox is rooted in modern set theory, especially in the use of what is called the axiom of choice. That axiom, which is central to many advanced proofs, allows the selection of elements from infinite sets in non-constructive ways. When it is applied to the geometry of a sphere, you obtain a decomposition so extremely intricate that no realistic physical method could replicate it. Put another way, the pieces into which the sphere is divided are not ordinary solid fragments, but extraordinarily scattered sets, with properties so peculiar that they defy our usual concept of volume. As a result, the conclusion is that the paradox cannot be carried out with real physical matter, but it logically and mathematically exists if we accept the postulates of set theory in a purely theoretical universe. To imagine this scenario in a more vivid way, first consider what decomposing a sphere typically means. We tend to think of neat cuts, as though slicing an orange into wedges. However, the Banach-Tarski paradox demands partitions that are not only infinitely intricate, but impossible to describe through standard geometric methods. These partitions rely on what are known as non-measurable sets, meaning sets for which no volume can be assigned under the usual sense of Euclidean geometry. The axiom of choice is what enables the formation of such sets. It allows you to choose points in the sphere in an entirely abstract way so that, in the end, you produce an extraordinary mathematical marvel. In broad terms, the procedure takes the sphere and splits it into a finite number of groups that, through certain rotations and translations, moves that do not change the size or shape of each piece, end up reconstructing two spheres identical to the first. Throughout most of history, up to the early 20th century, it was assumed this was impossible because it contradicted the law of volume conservation that traditional physicists and geometers relied on. In the real world, if you slice a ball and reassemble it, logic dictates that the sum of the parts is the original ball. But in the realm of set theory, where the concept of volume breaks down into infinitely unconnected points, that law ceases to hold. Still, the Banach-Tarski paradox depends on several assumptions that do not apply in physical reality. For one thing, it uses the geometry of three-dimensional Euclidean space. It also relies on the axiom of choice, which many do not view as intuitive, and involves the existence of non-measurable sets. Furthermore, it assumes that we can handle the resulting pieces without any limitations, as if they had no material cohesion. It cannot be done in spaces of fewer dimensions, for instance in a two-dimensional plane, where the requirements for these fantastic decompositions are not met. Throughout the history of mathematics, the presentation of this paradox led to tremendous excitement, revealing the tension between pure mathematics and our physical ideas of volume and matter. While it is not implementable with real physical objects, it shows the force of theoretical methods. It shows that the rules of set theory and measure can lead to conclusions that lie far beyond human intuition. Indeed, one of the paradox's main lessons is how it undermines our confidence in the idea that everything has a defined volume, or that you cannot get something out of nothing. To give a simplified example, think of trying to double the volume of a complex shape by moving some parts around. In everyday reality, we know that slicing and shifting does not change overall mass or volume, yet Banach and Tarski showed that if we use the axiom of choice to arrange extremely unusual non-measurable fragments, we can produce two copies of the same shape. It is as if, from one basketball, you could form two complete basketballs of the same radius as the original, simply by rearranging points. The violation of the usual sense of volume becomes clear. There is no way to give a volume in the standard sense to those pieces created by the axiom of choice, which breaks the usual paradigm. One lesson from this paradox is that Euclidean measure, that is, how we normally assign volumes, depends on structures that assume contiguity of sets and certain completeness properties. When you enter a territory with extremely disconnected sets, measure stops working as expected. Hence, the Banach-Tarski paradox is a reminder that much of what we consider obvious in geometry depends on underlying assumptions that can break down when the axiom of choice is introduced and non-measurable objects are allowed. Although this result does not violate physical laws, as there is no physical way to make such cuts, the paradox retains its quality of intellectual wonder. It underscores that pure mathematics can describe realities that do not align with anything we can physically construct. Some interpret it as a demonstration of how strange things can get once we accept the axiom of choice. That axiom, to emphasize its importance, allows, in an infinite collection of sets, the choice of one element from each, even if there is no concrete method for doing so. When such repeated selections occur in a space as large as a three-dimensional sphere, these non-measurable pieces appear, making possible the paradoxical doubling of a single ball. The Banach-Tarski paradox not only rattles our idea of volume and mass, but also pushes people to examine what proof or existence mean in mathematics. The fact that these decompositions exist does not mean there is an explicit way to construct them physically. It is a purely theoretical existence proof without providing a recipe that a geometric surgeon could follow. This is a scenario where the existence stems simply from logical consistency, showing that it is consistent to hold certain axioms, like the axiom of choice, even if they produce results at odds with physical intuition. Thus, it highlights the contrast between the space of mathematics and the physical reality in which we live, and how giving free rein to certain axioms can yield conclusions very distant from what we can build or experience tangibly. Some see this paradox as proof that mathematics does not always need to match the constraints of the tangible world. Others prefer more constructive or intuitionist approaches that reject such a powerful axiom as choice, fearing impossible consequences for real experience. Regardless, Banach-Tarski remains a definitive example of how far abstraction can go. It reveals that our usual statements like, "you cannot get more from the same matter," do not necessarily hold in every logical framework. Even if we cannot replicate it in a laboratory, the mental vision of splitting a sphere and ending up with two spheres of the same radius reminds us that mathematics can extend beyond every limit of our so-called common sense. What fascinates us is that by rearranging the particles of the sphere, points so minuscule and complicated that no typical volume notion can capture them, we end up with two entire copies of the original sphere. There is no mass exchange and no addition from outside, only a judicious use of the axiom of choice. The result directly conflicts with our perception of matter and space, yet remains unassailable within formal mathematics. Hence, the Banach-Tarski paradox is a lesson that our imagination in mathematics can transcend the bounds of what we call common sense. It urges us to consider the difference between the physical space we inhabit and the mathematical space we define with axioms, and it demonstrates that once you allow for certain axioms, you can arrive at truths vastly distant from anything physically realizable. The Berry paradox, the so-called Berry paradox, is one of the most intriguing examples of how language and self-reference can collide with logic and the notion of definability. It was discussed in the context of definition theory and the use of natural language to describe numbers, revealing a conflict that highlights the tension between verbal descriptions and mathematical formalization. The most striking aspect is how it weaves together a seemingly simple act of naming or describing a number, and the idea that doing so ends up creating a contradiction. To present the paradox, it's helpful to start with the phrase that typically triggers it: the smallest natural number that cannot be described in fewer than 11 words. The linguistic construction behind it is the key. It's an attempt to define a particular number using a clause that references the impossibility of describing it in fewer than 11 words. But almost immediately, one sees a critical point in saying the smallest natural number that cannot be described in fewer than 11 words. You might already have provided a description with fewer than 11 words, thus creating a clear contradiction. For instance, if you count how many words there are in the smallest natural number that cannot be described in fewer than 11 words, you might discover it doesn't exceed 11 words, leading to the contradiction of having defined in a short phrase, something that, by hypothesis, could not be defined in fewer than that number of words. To see why this causes a paradox, we first note the original motivation. When we say describe a number, we usually mean we can produce a statement or phrase that uniquely identifies that number. For instance, the number 1 can be described simply as the smallest natural number or the first natural number. The number 123 might be described as the number that is 100 plus 23. Thus, it seems we have ways to describe most natural numbers. However, the paradox arises when we ask if there is a number that cannot be described concisely, and whether we can refer to it indirectly to end up describing it anyway. The Berry paradox sits alongside other semantic and self-referential puzzles, akin to the liar paradox, though here it hinges on the definability or undefinability of numbers. The situation becomes complicated because natural language is so flexible. It seems to allow legitimate-sounding constructions that, upon analysis, turn problematic from a logical standpoint. One core element of the paradox is the supposed limit, namely, fewer than 11 words, for describing any number. On the one hand, there are infinitely many numbers, while on the other hand, natural language appears to have infinite descriptive resources. Yet any specific phrase is finite in length. Although many numbers might require very long expressions to define, the trick of the paradox is to say, the smallest natural number that cannot be described in fewer than 11 words. By that approach, we appear to define something that we initially said lacked a short description. In fact, there are variants stating the smallest number that cannot be described in fewer than 20 words in Spanish, or changing the exact number of words. The essence remains, by naming it with precisely that many words, one is giving a shorter description than what was claimed to be impossible, thus generating a direct contradiction. This kind of dissonance belongs in the category of semantic paradoxes, meaning it arises not so much from formal logic itself, but from how we use language to refer to certain objects. Mathematician and philosopher Bertrand Russell, among others, thought deeply about these kinds of issues. During the era in which set theory and formal logic advanced rapidly, it became evident that self-reference could introduce cracks into systems that otherwise seemed coherent. Russell examined the Berry paradox as an example of how tricky it can be to talk about describing a number in natural language. The usual solution or resolution to this paradox often states that the phrase, the smallest natural number that cannot be described in fewer than 11 words, is not a valid definition in a formal language nor a well-specified statement in the mathematical universe. Instead, it fails due to its self-referential nature and ambiguous phrasing. In other words, it is an exploit of language that doesn't strictly define what being described means or how to count words in a rigorous sense. Moreover, by insisting that a number cannot be described, yet seemingly describing it with that very phrase, we run directly into a logical inconsistency. The central aspect is that in arithmetic or formal definability theory, you can't simply say definable without a very precise framework, a formal language, a given set of axioms, a system for forming definitions. When you try to blend these ideas with the flexibility and richness of natural language, which can craft expressions that are indefinite in length and self-referential, you open the door for contradictions such as the Berry paradox. Thus, many see it as illustrating the need to keep formal mathematical discourse, with its tightly regulated vocabulary and syntax, separate from natural language, which is ambiguous and easily leads to paradoxes. On a more intuitive level, Berry's paradox reveals how easily seemingly effective descriptions can turn out not to be truly effective definitions. The phrase, the smallest number that cannot be described in fewer than 11 words, looks like a valid definition at first, but has a logical loop. If it actually designates a number in so few words, then that number can be described in fewer than 11 words, contradicting the statement that it cannot. In areas such as information theory or definability complexity, people debate how to formally circumscribe the process of describing objects. They'll discuss the length of a description in a specific formal language, like a programming language or a formal mathematical theory, by counting bits or symbols. Yet if we extend that idea to a natural language like Spanish or English, we re-encounter issues of interpretation and ambiguity. Natural language supports synonyms, rephrasings, and compressions that can unexpectedly make a definition more concise, so the entire notion of a non-describable number with a set limit of words becomes even more complex. The effect this paradox has on those interested in logic and philosophy of language is akin to the reaction sparked by the liar paradox. Both revolve around self-reference. The statement or definition references its own impossibility or its own truth-falsity. In Berry's case, it points out the impossibility of describing a number in fewer than a given number of words, and then that very phrase might itself accomplish such a description. This vicious circle demonstrates the destabilizing power of self-reference if it's not controlled by strict formal guidelines. Hence, Berry's paradox underscores how easily natural language can lead to contradictions, highlighting the necessity for carefully designed formal systems whenever one wants to avoid such quandaries. Furthermore, it invites us to question how casually we may say the smallest number that satisfies this, or the largest number that doesn't do that. These linguistic acts, seemingly innocuous, can harbor logical traps if not handled carefully. Unlike certain other paradoxes like Monty Hall or Zeno's arrow, which involve some numerical or physical conflict, Berry's paradox centers on semantics and linguistic logic. Its impact doesn't come from a numeric result that defies our intuition, but rather from the realization of a logical short circuit in the verbal definition of a mathematical object, or a number. This is why it's viewed as a perfect case of a semantic paradox, connected with definability problems and self-referential paradoxes. Some regard the Berry paradox less as a true paradox, and more as an example of how natural language, replete with ambiguities, can create contradictory statements when used to talk about mathematical objects. But that doesn't diminish its ability to stimulate reflection about the infinite, about language, and about the tension inherent in describing numbers or sets. It also shows how simply combining a certain number of words with definition of a number can open the door to conceptual pitfalls that, if unregulated, lead to contradictions. And it is precisely that tension that fuels the surprise and drives people's fascination with it, demonstrating that the realm of paradoxes extends beyond physical calculations into the foundations of discourse and semantics. The Bertrand Paradox. The so-called Bertrand Paradox is a classic example in geometry and probability theory that shows how the notion of choosing something at random can be deceptive if we do not rigorously define what random means in a particular context. Formulated by the French mathematician Joseph Bertrand in the 19th century, it involves a thought experiment asking for the probability that a chord, supposedly selected randomly on a circle, has a length greater than that of the side of an equilateral triangle inscribed in that same circle. The outcome turns out to depend on the method used to generate the chord, leading to different probability values and giving an appearance of contradiction. To lay out the situation clearly, imagine a circle of a fixed radius. We want to draw a random chord on it and ask, what is the probability that this chord is longer than the side of the equilateral triangle inscribed in that circle? It is known that the side of such a triangle is equal to the square root of 3 times the radius if we measure properly. Therefore, the question is which fraction of possible chords exceed that particular length. The puzzle arises when we realize that there are several ways to define a chord drawn at random. Each method ends up providing a different probability, which produces a seeming inconsistency or paradox, because one would think that the question, what is the probability that a chord is longer than the side of the equilateral triangle, should have a unique answer, not dependent on the procedure. Yet the paradox demonstrates that random is not a universal concept, and that if we talk about choosing a chord at random, we need to specify precisely which selection procedure we are using. At least 3 common ways of defining this selection exist. Midpoint method. Take the circle and choose the midpoint of the chord at random inside the disk, assuming that the midpoint's location is uniform over the area. Then, define the chord whose center is that point. Angular endpoints method. Choose 2 points on the circumference by selecting angles uniformly between 0 and 2 pi, and connect those 2 points to form the chord. Here the randomness is in picking angles with a uniform distribution from 0 to 2 pi. Radial chord method. Select a radius of the circle at random, then choose a point on that radius with a uniform distribution between the center and the perimeter, and draw the chord perpendicular to the radius at that point. Thus the midpoint of the chord lies at that chosen position on the radius. Each of these methods is considered natural or legitimate for defining a random chord, and yet each yields a different probability result. The Bertrand Paradox refers to the fact that the statement, "a chord chosen at random," is not fully specified unless we clarify which one of these or other procedures is being used. That is the heart of the problem. The notion of randomness in geometry can require additional definitions to remove ambiguity. To illustrate the conflict in more detail, one method might produce a probability of 1/3, another might produce 1/4, and without changing the basic question, a third might give 1/2 or some other value. The discrepancy among these values underscores the idea that no single uniform distribution for chords exists. Different plausible choices of randomness imply different probabilities. Behind this paradox is the distinction between the measure of angles, the measure of midpoints, and other forms of uniformity. For example, choosing the angular endpoints uniformly around the circumference differs from choosing the midpoint uniformly in the area of the disk. It is precisely those different mathematical constructions that give rise to disparate outcomes. Therefore, it is not that one result is wrong, but that each refers to a different conception of drawing a chord at random. More broadly, the Bertrand Paradox underscores the discussion about how to define geometric randomness. This has implications not only for simple problems like drawing a chord, but also for interpreting continuous models in physics and for statistics concerning random variables in symmetric spaces. It serves as a reminder that before we answer what is the probability of such and such event, we must carefully specify how the event is generated. This paradox also reveals that our sense of probabilistic fairness is strongly tied to the mental representation we have of the process. If someone imagines every angle is equally likely, they adopt a different method than if they consider every possible midpoint in the interior is equally likely. Each one can be seen as a plausible idea of random, but they lead to incompatible conclusions. This phenomenon shows that analytic geometry and measure theory actually contain diverse ways of talking about uniformity, and these methods need not coincide. From a pedagogical perspective, the Bertrand Paradox is often used to emphasize the importance of specifying assumptions in a geometric probability problem. If the exact protocol is not stated, for example, pick one endpoint's angle uniformly, then pick another endpoint's angle uniformly, the question, what is the probability that the chord is longer than a certain length, remains open. The final divergence of results is not a logical flaw, but an indication that the question as posed was incomplete. Historically, Joseph Bertrand proposed the paradox at the end of the 19th century to highlight precisely this ambiguity. Since then, people have offered multiple interpretations. Some say one method is the most natural, others defend a different one, but there is no universal consensus because it depends on how one defines the random chord. For some, the simplest method is to pick 2 points on the circle with angles uniformly distributed. For others, it is to choose the midpoint uniformly within the disk. For still others, it is to choose a radius and then pick a point along it. Each approach is related to a certain notion of symmetry. Selecting angles uniformly suits polar symmetry, whereas picking the midpoint uniformly suits area-based symmetry. When the method changes, so does the probability of length being greater or length being less. One frequently repeated observation is that a casual observer might find it perplexing that such a straightforwardly phrased question, "What is the probability that a chord measures more than some specific length?" could lack a unique answer. In fact, we are accustomed to thinking that in probability questions there should be a single, correct, numeric solution. Bertrand's paradox shows that absent a precise statement of how the chord is chosen, the problem is underspecified. The contradictory results are not randomness run amok, but rather a sign that we are dealing with different definitions of the same question, each with its own set of assumptions. This does not mean probability is arbitrary, it means our question was too vague and omitted critical details for pinning down the distribution. Hence, the paradox is not a logical error, it is a valuable illustration of the importance of clarity in the concepts of randomness and measure when dealing with continuous problems. Moreover, the paradox stands as a reminder that while geometry can appear intuitive, a random chord is just any chord, right? The meaning of any chord or random chord is multifaceted. One might think that all chords are equally likely, but that seemingly direct phrase conceals multiple interpretations. Each approach to modeling that scenario yields a distinct result. This underscores the complexity of translating the abstract notion of uniformity into a practical example. Another point often underscored is that, for someone less specialized in mathematics, it can be puzzling that a question as trivial sounding as a random chord can lack a single, unambiguous answer. We typically operate under the assumption that the question, "What is the probability of X?" always yields a single number. Bertrand's paradox underscores that, without thorough specification of the selection process, how we define random chord, we can get contradictory answers. The paradoxical nature arises because we assumed there was a unique right answer, yet in truth it reflects an incomplete question rather than a flaw in logic. Thus, the Bertrand paradox is a crucial case study in geometric probability, teaching us that random must be carefully described to avoid contradictory conclusions. Its paradoxical air arises from the mismatch between our expectation that there is a single outcome and the reality that different, reasonable definitions of randomness lead to different probabilities. It is neither a sign of chaos nor of failure, but rather proof that the method by which we define the random experiment is essential. This shows that in geometry or in any continuous setting, the slightest shift in how we define random choice can have a substantial impact on the final probability. The twin paradox. Among the most famous topics discussed in special relativity is the so-called twin paradox, a thought experiment that underscores an apparent contradiction when two symmetric observers each seem able to claim that the other one is in motion, yet upon reuniting, only one sibling has aged less than the other. For many people, this scenario becomes the prime illustration of the clash between our everyday intuition and the postulates of relativistic physics put forth by Albert Einstein at the start of the 20th century. To frame the situation, we picture two twin siblings. One remains on Earth and the other sets off on an interstellar voyage at very high speed, close to the speed of light. After some time, the traveling twin returns and they meet again. According to calculations from special relativity, the traveling twin, because of time dilation, is younger than the one who stayed on Earth. This appears to have an initial symmetry, since each twin might say, "I see the other one moving," which leads to the question, why then is it not the case that each sees the other aging more slowly, ending up the same age when they're back together? To understand the paradox, one must recall, in short, the basics of special relativity. There is no absolute reference frame. Motion is always relative. Every inertial observer, that is, one not accelerating, can consider themselves at rest and see others moving. At speeds close to the speed of light, time dilates. If observer A sees observer B moving, A can calculate that B's clock is running more slowly. The apparent contradiction stems from the idea that each twin sees the other in motion, so one might expect a total symmetry. But the main resolution to the twin paradox is that the traveling twin performs a change of reference frame when turning around to come back to Earth. This twin does not stay in a purely inertial state. They experience acceleration and deceleration when leaving Earth, turning around and returning. Meanwhile, the twin who remains on the planet never leaves, or at least ideally, remains in an inertial frame, assuming we treat Earth as approximately inertial compared to the spaceship. That fact breaks the presumed symmetry, revealing that their situations are not equivalent. Hence, the premise that each sees the other moving is not fully valid when one sibling's world line involves acceleration and the other's does not. To elaborate, from the Earth-bound sibling's perspective, the traveling twin moves at high speed, experiencing a strong time dilation. Every second on the ship transpires more slowly compared to every second for the sibling who stays home. At the same time, when the traveling twin describes their own experience, they note that during the outbound phase, they might see Earth's clocks as ticking more slowly, but upon the turnaround, the maneuver to head back, they switch frames of reference, and that breaks the straightforward notion of inertial relativity and introduces a more complex analysis of simultaneity. Ultimately, the traveling twin truly finds that upon returning, Earth's time has advanced further overall. In simpler terms, the key is that the traveling twin disconnects their inertial temporal coherence at the instant of turning around. This abrupt return acceleration causes, within their frame, a radical shift in how they define simultaneity, suddenly jumping Earth's timeline forward in the traveler's view. So, upon return, the traveler sees that their sibling has aged more overall than it first appeared. During the initial phases of travel, it may help to imagine a space-time diagram showing the path or world line of both twins. The Earthbound twin stays roughly in fixed spatial coordinates, while the traveling twin's path moves away and then comes back. Visually, the traveling twin's world line is shorter if measuring proper time, the traveler's own elapsed time, whereas the straight-line path of the Earth twin maximizes that proper time within the geometry of space-time. Special relativity states that at higher velocity, time dilates, and that the path involving acceleration and a turnaround accumulates less proper time compared to remaining inertial. One of the fascinating aspects of this paradox is how it captures the apparent contradiction. If motion is relative, why is there no reciprocal aging effect? Often the answer is summarized by saying that there is no perfect reciprocity because only one twin undergoes acceleration. Even if that acceleration is brief, it does exist, thereby breaking the fundamental equality of physical conditions. Meanwhile, special relativity says that only inertial frames, without acceleration, strictly maintain each sees the other in motion. Once acceleration enters the picture, you're no longer in the same inertial frame and must analyze the trip by slicing it into multiple inertial segments, or, if you prefer a more advanced approach, use general relativity for a fuller treatment of acceleration's role. The twin paradox isn't just a short anecdote. It has fueled countless pedagogical and philosophical discussions, plus indirect experiments that confirm time dilation. At a smaller scale, precise atomic clock tests have been done, Taking a clock on a high-speed airplane and comparing it to a clock left on Earth shows that the airborne clock accumulates less time, matching the relativistic predictions. These experimental results reinforce the theoretical description and demonstrate that, rather than a contradiction, it's a logical consequence of relativity. Obviously, any real-life difference in the twins' ages is typically tiny, as the traveler's velocity might be high but not nearly high enough to produce a dramatic effect. Still, the paradox's main power is in highlighting how simultaneity and the passage of time aren't absolute but vary strongly with the frame of reference. When an observer switches frames, it also changes how they see the other's time unfold. A further interesting point is that one might simplify the story by saying the ship speeds away, then comes back, accelerating and decelerating. But in a more nuanced approach that avoids general relativity, one can divide the journey into several inertial stages, each at constant velocity, interspersed with sudden jumps to change velocity. Summing up these partial inertial segments gives the same result. The traveling twin experiences less total proper time than the Earth twin, consistent with the geometry of Minkowski spacetime. Even with this step-by-step approach, you end up concluding that the traveling twin is younger upon reunion. Regarding intuition, people often cling to the idea that, from the traveler's viewpoint, the other is moving too, expecting perfect symmetry. But a closer look shows that during the journey, the traveler cannot keep making that statement the same way, since their reference frame is not single or purely inertial throughout the trip. It undergoes major acceleration at the turnaround, invalidating any claim of full symmetry. Therefore, only one twin ends up younger, and that is genuinely the one who moved and switched frames, with no equivalent effect for the other, who remained stationary or in uniform motion, if we speak more rigorously. Some mention that if both twins took equally accelerated and symmetrical journeys, for instance, they both move away from each other and then come back, then indeed they might end up with the same age. Yet that's not the classic scenario where one stays home, the other travels. Ultimately, this paradox does not violate special relativity but compels us to apply its principles carefully, noticing that the acceleration disrupts perfect reciprocity. The prime lesson is that time is relative, and each observer's lifespan is determined by their path through space-time, such that a path taken at high speed and with turnaround can accumulate less elapsed time. Culturally, this notion has often been used in sci-fi contexts. The traveling sibling returns after a century, while the Earth sibling is an elderly person. Even though it's hard to achieve significant effects in practice, the smaller scale verification of time dilation has been extensively proven. Thus, the twin paradox remains a top-tier example of how special relativity upends our intuition. It teaches us that not all motion is symmetrical, and that experiencing less aging is no mere illusion, but a tangible outcome when one follows a path involving relativistic speeds and acceleration. For those who dig deeper, it also shows that reality for each observer is defined by their particular path through space-time, and that when you alter that path by changing velocity, you introduce a genuine asymmetry in what once seemed symmetrical. The scenario's appeal comes from its simple narrative, only two twins, one trip and a reunion, yet it raises fundamental questions about time and distance, matters that had seemed absolute before Einstein. That makes it a pillar in relativity teaching and a constant reminder that the universe's laws can differ greatly from what we find logical, straightforward, or natural based on everyday experience. The Grandfather Paradox. Among the most iconic examples in the context of time travel is what's known as the Grandfather Paradox. It's posed in a seemingly straightforward manner. Imagine you manage to travel into the past and for some reason you prevent the birth of one of your direct ancestors, often illustrated by the idea of killing your grandfather before he can father your parent. By doing so, you create the contradiction that you would never have been born to carry out that act in the first place, since your own existence depends on your ancestors having lived and reproduced. Although it might sound like a simple sci-fi tale, this scenario showcases one of the most profound dilemmas regarding causality and temporal coherence. Broadly speaking, the paradox asks how the timeline can remain consistent if a person can intervene so drastically in past events. The classic image is that of a time traveler who chooses, for various motives, to prevent the meeting of their grandfather and grandmother or to cause the grandfather's death before the next generation is conceived. The immediate result is that the traveler would never be born in the future, so they could not have traveled back to commit the act. Thus, a logical loop arises in which the event, the trip and the action, negates itself, contradicting a consistent history. For many, this scenario relies on the assumption that there is only a single timeline, a single universe, in which events unfold in a linear and irrevocable manner. Within that timeline, if you eliminate the conditions of your own existence, a contradiction inevitably emerges. Over the years, multiple theoretical solutions have been proposed in an attempt to reconcile traveling to the past with causal coherence, though there is no consensus in mainstream physics that such travel is physically realizable. Still, the paradox has spurred debate both in science and in philosophy. One early strategy in science fiction is the notion of multiple universes or timelines. In this view, when you travel to the past and change the event that leads to your family line, you do not modify your original past. Instead, you initiate or enter an alternate timeline in which your grandfather does not have offspring. You, however, who come from the original timeline, keep existing since you belong to the earlier history where your grandfather did indeed live and have children. This thus avoids the contradiction in your own chronology, but it implies the creation of parallel realities or branches in history with every time travel intervention. Some see this model as involving an ever-growing array of alternate realities. Another much discussed approach is the idea of self-consistency, the argument that if something threatens your birth, somehow that act never comes to fruition. The universe, so to speak, prevents any occurrences that would produce unavoidable paradoxes. Perhaps you shoot at your grandfather but the shot always misses, or some unexpected factor intervenes so that you fail in your intention. Thus, the timeline remains consistent, and you never genuinely manage to obliterate the reason for your existence. Often tied to Stephen Hawking's chronology protection conjecture, this assumption states that nature blocks paradoxical outcomes, making it impossible to alter events that guarantee your birth. Literature and film abound with variations on this paradox. For instance, a character might try to eliminate a dictator before that dictator commits atrocities, only to discover that their actions, far from averting the disaster, end up causing it. Or inversely, they unintentionally become the very trigger for what they aimed to stop. The grandfather figure is simply the most direct metaphor for illustrating the ancestral line that leads to the traveler's own birth. From the standpoint of relativity and modern physics, the grandfather paradox intersects with the possibility, in principle, of closed time-like curves, an allowance in general relativity for certain exotic spacetimes, like wormholes or rotating universes. Yet many physicists suspect that some undiscovered physical principles or the complexity of quantum gravity would prevent real-world achievements of this nature. Therefore, many treat these paradoxes as hypothetical constructs rather than feasible phenomena. Still, no definitive consensus exists on the matter. Conceptually, the paradox is easiest to grasp as a direct challenge to causal logic. In a classical, deterministic world, we know effects come after causes. But traveling back in time implies a chance to revisit and alter the cause, leaving the effect, your own future existence, up in the air. This contradiction slices to the heart of how we perceive the arrow of time and the structure of space-time. Approaches that allow for multiple timelines or enforce self-consistency aim to manage that crisis. Beyond the core causal issue, the grandfather paradox also resonates with reflections on personal identity. If wiping out your grandfather equals erasing yourself from history, it raises the question, what defines who I am through time? It furthermore leads to moral dilemmas. Eliminating your ancestor is arguably a very special form of murder, since it can wipe out an entire lineage. Some stories depict a time traveler fixated on undoing a tragedy or historical mistake, unaware that doing so threatens their very existence. Again, the paradox emerges. There is no way to fix that past event without negating yourself in the process. One interesting angle is the conversation between free will and determinism. If the traveler vows, "I will do whatever it takes to kill my grandfather," and the universe thwarts them, that might suggest their freedom is limited. Perhaps they genuinely cannot accomplish that deed, although they do not realize why. This scenario points toward the possibility that the timeline is not malleable, like a block universe, such that all attempts leading to paradox end up failing or self-correcting. Thus arises further philosophical debate about whether the future is somehow locked in to maintain historical coherence. Narratively, the grandfather paradox has become emblematic of time travel fiction. Often the plot centers on how a main character wants to fix their past or their family's past, but encounters the logical impossibility or unforeseen side effects that eventually restore consistency. Other tales adopt the parallel worlds path, with the traveler returning to a changed present or discovering they can no longer revert to their original timeline. Meanwhile, the original reality from which they departed presumably continues or becomes inaccessible to them. The central crux of the paradox is not just the shock value of killing one's grandfather, but the tension between free agency and a unified historical narrative. If time were truly malleable, why cannot one simply eliminate the conditions of one's own birth? But if nothing stops such an act, how does one explain a reality in which the traveler already exists? Consequently, the situation is called paradox, though strictly it's a question about reconciling time travel with linear causal logic. Some authors propose resolving it by describing how the universe self-reflects, so that any meddling in the past won't create a timeline that invalidates the cause, but rather channels events so that those crucial outcomes remain intact. In certain versions, the traveler thinks they succeed in killing their grandfather, yet later learns the person they killed was not their real grandfather, or that the genealogical line continued via other circumstances. This and similar plots highlight how attempts to break the chain of cause and effect fail, preserving coherence. On a theoretical level, discussions about the grandfather paradox intensify when factoring in quantum theories, such as notions that at a quantum level trajectories might not be fixed, allowing backward-in-time interactions without a global inconsistency. Yet all of this remains highly speculative, given that current physics does not offer a unified agreement on any real form of backwards time travel. For many, the existence of this paradox is itself evidence that such travel is physically impossible, absent exotic solutions that might never be realized. Still, the paradox draws philosophical and popular interest because it prompts us to rethink what changing history entails and fundamentally what free will or determinism mean if we can revisit events already believed to be unchangeable. Meanwhile, the outward simplicity, "what if you went back and stopped your grandfather's marriage?" reveals how easily logical absurdities can arise once the possibility of time travel intervention is introduced. Thus, the grandfather paradox underscores the boundaries that logic and causality set if we imagine going back to the past to alter key happenings. Contrary to a romantic view, just prevent this event and everything is different. The paradox insists on the impossibility or incoherence of actually bringing about that modification, or else demands more complicated postulates, like the splitting of universes or a principle of self-consistency preventing the final paradox. Consequently, it occupies a central place in reflections on the nature of time, free will, causality, and coherence, heavily influencing sci-fi works and speculative theories that push the frontiers of our grasp of the universe. Littlewood's Paradox. Among the wide variety of paradoxes that illustrate outcomes at odds with our intuition, there is what's known as Littlewood's Paradox, related to infinite processes and the manipulation of time-based sequences that lead to seemingly absurd results. This paradox typically refers to situations where certain actions are repeated an infinite number of times within a finite span, culminating in an outcome that defies our expectations about the continued presence of certain elements over time. Although it might not be as popular as, say, Banach, Tarski or Monty Hall, Littlewood's Paradox also examines the limits of our intuition when dealing with infinite series and the notion of an end to a process. To understand it, it helps to outline one of the scenarios commonly used as an example. Picture a large container, or urn, and an infinite collection of numbered balls, ball 1, ball 2, ball 3, and so on, covering all natural numbers. Next, you define a process with a sequence of time intervals. In the first interval, maybe lasting half a minute, you insert some balls into the container and remove others. In the second interval, a quarter of a minute, you do something similar and so forth, with each interval getting briefer. If the sum of these intervals converges to a single minute or 2 minutes, then after a finite time, you will have performed infinitely many steps. The paradox arises when, according to the rule for putting in and taking out balls, it turns out that at the end of the process, i.e., once that finite time has elapsed, no balls remain inside the urn, or we arrive at some other outcome completely at odds with what we might expect from the sum of these seemingly constructive actions. A typical straightforward version might say that at each step you add 10 new balls and remove 1. Intuitively, you would think that, after repeating this many times, the number of balls in the container would increase or at least never drop down to 0. But if each step is assigned a time interval that shrinks quickly enough so that in a finite span, say 1 minute, you have executed infinitely many steps, the end result can be that despite having introduced a huge number of balls, you end with an empty urn. How is that possible? The explanation hinges on the fact that in each stage you remove a specific ball, for instance, the one whose number matches the step number or follows some other pattern, ensuring that over the course of infinitely many rounds, every ball ever introduced is eventually removed. If, at step n, you remove ball number n, then there is no ball that avoids being taken out at some point during the infinite series. Consequently, after all steps are done, no ball remains at the end, even though infinitely many were added along the way. This construct directly derives from the idea of numbering the balls and assigning a definitive moment to remove each one, making sure that none is left unaccounted for. The paradoxical aspect lies in the contradiction between, on the one hand, constantly adding more and more balls, an apparent accumulation, and on the other, seeing that in the completed process, once we surpass all infinitely many steps in a finite time, every ball does, in fact, get removed at some stage. You conclude with an urn that is empty. Therefore, Littlewood's paradox deals with a situation in which an infinite number of steps is completed in a finite amount of time if those steps occur in intervals whose lengths decrease fast enough for their total to converge. It's reminiscent of how geometric series work, 1/2 plus 1/4 plus 1/8, etc., sums to 1. Thus, in the first half minute you do the first action, in the next quarter minute you do the second, in the following 8th minute the third, and so forth, so that by the end of a single minute you have carried out infinitely many actions. the source of the puzzlement is much like that of other paradoxes related to convergent infinite series or supertasks. A supertask is any scenario in which an infinite set of actions is performed within a finite duration. Our day-to-day instincts say it is impossible to complete infinitely many steps in such a short time, but mathematically, if the intervals get short quickly enough and the rule for assigning which balls are removed is well defined, the outcome defies that initial intuition. There are multiple variations of the paradox that tweak how many balls are introduced, how frequently, and how they are removed. They all share the same core structure. They use an infinite set of objects, the numbered balls, and a distribution of shrinking time segments to execute a process with a surprising end. In some versions, you can likewise end up with infinitely many balls in the container, or some other number than you might expect, depending on the details of how you add and remove. Another instructive aspect is how the paradox highlights the notion of a final moment in an infinite process. Typically, we think that if in each finite phase we add more items, we'll see an overall build-up. But a supertask with a well-crafted design can subvert this intuition if each inserted item is eventually removed. After infinitely many steps, taking place in a finite time, everything is gone. In a more precise discussion, each ball n is removed in step n, guaranteeing that there's no ball without its assigned removal step. After all infinite steps, the set of remaining balls is empty. Yet if someone at any instant during the earlier stages checked the contents of the urn, they would have found plenty of balls inside. The subtlety is that only upon completion of the infinite series of steps, meaning once every step n has occurred, can we say there are no balls left. That's the distinction between what happens at each finite stage versus what happens at the limit after infinitely many steps. Physically or practically, one can argue that such an experiment is unattainable. We can't realistically speed up a process of adding and removing balls ad infinitum in intervals that sum up to a single minute, nor can we surgically ensure each ball is eventually removed by some step n. But in pure mathematics, there is no contradiction, so long as the definitions are carefully laid out and we accept the logic of infinite sets. Some compare this to Zeno-like paradoxes where infinitely many steps occur in a finite period. Each step is half as long as the previous one, so the total time converges. Littlewood's paradox adds an infinite set of objects, the numbered balls, plus a method of removing them in a precise sequence that results in an empty urn at the limit. It's the merging of those two infinities, actions, objects, within a convergent time series that makes the final state so astonishing to basic intuition. Didactically, the paradox underscores the gap between what happens at every finite step and the situation at the end of the infinite sequence. Our everyday thinking usually assumes we accumulate something if we steadily add it over time, but a supertask can reverse that logic if each element eventually meets its moment of removal. It also exemplifies a powerful one-to-one correspondence principle with the natural numbers, saying, during step n, we remove the ball with label n, sets up a direct matching where each ball definitely leaves the urn at its own step. Hence, there is no stray ball left after infinitely many steps. Formally, this is flawless. Physically or intuitively, it can feel bizarre to see infinitely many added, yet end up with an empty container. What Littlewood's paradox ultimately conveys is that combining infinite tasks, adding infinitely many elements, with correspondingly infinite removals done within a finite time, leads to results that defy our everyday assumptions. It's precisely because we never experience these infinite processes in real life that we find such results shocking. But mathematically, from a perspective of carefully defining sequences of events, there is no contradiction, just the rules of logic applied to infinite sets of intervals and actions. In short, Littlewood's paradox highlights the difference between, at any particular stage, and after the limit of all infinite stages. As long as the last step is never fully reached in finite time, we keep seeing plenty of balls. Once we do cross that boundary, the limit, we discover each ball had its designated removal. Thus, Littlewood's paradox stands as a vivid reminder of how infinite repetition of certain small actions can overturn common sense, and how crucial it is to clarify definitions of time and infinity to avoid confusion. For teaching series theory or the nature of infinity, this example is especially striking. It can surprise, fascinate, or annoy newcomers who see it as akin to magic. Where did all those infinite balls go? But under formal mathematics, everything is consistent. It merely relies on one-to-one correspondences and time intervals decreasing in a convergent sum. In that sense, Littlewood's paradox prompts us to rethink the usual view of continuous processes, the invariance of accumulation, and the way a completed infinite task within a finite span can yield shocking conclusions. Fitch's paradox. Among the many paradoxes that arise when delving into the subtleties of logic and epistemology, there is what is known as Fitch's paradox. Often presented as a conflict between the idea that all truths are in principle knowable and the resulting conclusion that all truths are in fact known, it initially sounds completely unreasonable. At the heart of the paradox lies the combination of assumptions about the possibility of knowing every truth with a certain modal logic describing how the possibility of knowledge can imply the actuality of knowledge. To lay out the paradox, one should recall that it emerged in the context of verification theory and the debate over potential omniscience versus actual omniscience. Put more simply, there is a thesis sometimes called epistemic anti-realism, or the knowability thesis, which posits that any true proposition is in principle accessible to human knowledge, or at a metaphysical level to the cognition of some agent. That is, there would be no truth that is in principle hidden forever. If something is true, it can at least possibly be discovered. However, Fitch's paradox suggests that if one formalizes that idea within an epistemic modal system, one deduces not only that every truth is potentially knowable, but that every truth is in fact known, a result that collides with the intuition that many truths remain unknown, uninvestigated, or may never be discovered. In more precise terms, the paradox merges an assumption of the type: for every proposition P, if P is true, then P is potentially knowable, with an epistemic modal logic employing a notation like KP to mean P is known. One rewrites the statement as, for all P that are true, there exists the possibility that KP could hold. By adding that the conjunction P and not KP, i.e. P is true but not known, is also presumably knowable in principle, one ends up with a conclusion that no true but unknown proposition can exist. In short, the compatibility of the knowability thesis with the logic at hand compels the conclusion that there cannot be a proposition that is true yet unknown, so every truth must already be known. This outcome clearly seems absurd, since it implies a kind of universal omniscience, as though there were no facts left undiscovered. One might think that if something is true but nobody knows it, it could still be, in principle, knowable. Yet the paradox claims that melding that idea with the requirement that any unknown truth be, in principle, knowable, leads to a logical disaster. Either there is no proposition that is both true and unknown, or we discard the original principle of universal knowability. The first option, there is no unknown truth, is obviously nonsensical. The second undermines the original idea that every truth can be known in principle. We often call Fitch's paradox the argument for omniscience, because formally, if we accept that all truths are knowable, we end up concluding that all truths are actually known right now. It thus strikes a blow at the distinction between knowable and actually known. More specifically, a large part of the proof centers around the proposition P and not KP. Under the knowability thesis, if P is true, then P and not KP should be knowable in principle. But once one assumes it is possible to know P and not KP, it sparks contradictions in epistemic logic, because if one comes to know that P is true and that it is not known, the very act of knowing it undoes the not KP portion. That self-reference brings the system down. It's akin to other semantic paradoxes where the action of knowing or defining something alters the condition being described. Like other logical puzzles, the paradox may be resolved by relaxing or reworking certain premises. A commonly discussed escape is restricting the notion of possibly knowable to exclude propositions that transform themselves upon being known. Thus, one may rule out statements of the style P and not KP. Another option is to say that the knowability principle is intended only for an ideal agent, free from the constraints that create these self-referential troubles. However, that also prompts debates about how meaningful a knowability principle is if certain statements causing those issues are excluded. The main controversy is whether Fitch's paradox undermines the universal knowability thesis or simply reveals the naivete of a formulation that fails to distinguish between all true statements and all true statements that remain true if recognized. In epistemic logic, the usual conclusion is that one cannot consistently hold that every true proposition is potentially knowable while also insisting that some of those true propositions remain unknown. Once we test P is true and nobody knows P, the scenario collapses under formal scrutiny. Philosophically, the paradox has significance in discourses on verificationism, which says that truths not verifiable are meaningless or lack genuine status. According to that stance, all truths are potentially verifiable. Fitch's paradox points out that once formulated logically, this principle implies everything is indeed verified, undermining the idea that we can have countless truths outside our knowledge. Hence, many see Fitch's paradox as a major blow to certain versions of verificationism, or at least a prompt for major refinements. From a practical standpoint, we ordinarily assume there are infinitely many truths we do not know, details about the universe, historical occurrences lost with no record, future phenomena yet to be experienced, and so on. Fitch's paradox does not empirically challenge that. Rather, it indicates that if we combine the statement that every truth is knowable with robust modal epistemic logic, we inevitably arrive at every truth is known, which clearly contradicts real life. Thus, for many, this means that the universal knowability thesis, at least in that formal sense, is unsustainable. Crucially, self-reference and state change upon knowing the proposition are at play here. The expression P and not KP becomes the case where, if someone were ever to know it, the part not KP would stop being true. Analogous to other semantic paradoxes like the liar or bury, where describing or defining something disrupts the property in question. Some see Fitch's paradox as a warning about the nuances of modal logic in epistemology, emphasizing that being potentially knowable is not the same as being knowable without altering the statement's condition. In simpler words, there may be truths that, by the very act of trying to identify them, are no longer in the same state as they were when unknown, somewhat reminiscent of quantum phenomena where measurement changes the observed system, albeit more as an analogy than a direct equivalence. Pedagogically, Fitch's paradox illustrates the force of epistemic modal logic and the importance of precisely defining epistemic hypotheses. If one defines for every true statement P is possibly known, and also allows that P and not KP is possibly known, one concludes there is no P that is unknown. This outcome yields the sense that the universal knowability thesis collapses or at least must be reformulated to avoid that paradoxical conclusion. One can make an analogy that Fitch's paradox also targets certain forms of epistemic idealism where we say any truth can be discovered by a sufficiently capable mind. Fitch's demonstration says that if you adopt that stance naively, you end up implying instantaneous universal omniscience. Therefore, we must carefully separate the possibility of learning something from the actuality of it being known right now. Failing to do so yields this paradox, and in philosophical discourse, the paradox resonates beyond pure logic. Many discussions about empirical verification, the limits of human knowledge, and the existence of so-called unknowable truths revolve around the concept that not all truths are accessible. Fitch's paradox, while not a practical hindrance to scientific research, reveals that a statement like "every truth is discoverable given enough conditions" can have unacceptable logical consequences unless we carefully refine its scope. Historically, the paradox is linked to philosopher Friedrich Fitch in the 1960s, who explored the relationship between knowledge and truth within an epistemic logical framework. Although less famous in mainstream circles than certain more tangible paradoxes like Schrödinger's cat or Zeno's arrow, it has generated much academic literature on how, or whether, to avoid instant omniscience under the premise of universal knowability. In short, Fitch's paradox is both simple and striking. If we assume that every truth P is possibly known, we end up deducing there are no unknown truths, which seems blatantly absurd. Its moral is that epistemic postulates combined with modal logic can yield conclusions that run directly counter to our intuition that there must exist numerous truths lying beyond our grasp. The paradox forces us to clarify how we define knowable, truth, and knowledge status. And it warns us not to conflate possibility with actuality, especially where acknowledging a proposition might change its own condition of being unknown. Newcomb's paradox. Among the most debated riddles at the intersection of decision theory, the philosophy of rationality, and logic, we find what is called Newcomb's paradox. Formulated by the physicist William Newcomb, but popularized by the philosopher Robert Nozick, it revolves around a hypothetical game featuring an infallible predictor who anticipates our choices. The paradox hinges on whether it is preferable to pick only one box or two boxes, and to what extent faith in the predictor's ability alters what we consider the rational decision. To situate the paradox, imagine two boxes before you. Box A, opaque, which may contain either 1 million monetary units or nothing at all. Box B, transparent, which always contains 1,000 monetary units in plain sight. The rules specify a being called the predictor, which apparently makes extremely or perfectly accurate forecasts, has already made a prediction about what you will do. Based on that prediction, it placed or did not place the million in box A before you arrived. After this process, you come in and may either pick only box A or take both boxes. If the predictor anticipated that you would choose both boxes, then it would not have placed the million in box A. If, by contrast, it predicted that you would pick only box A, it would have put the million there. The choice regarding box A's contents was made prior to your arrival, and you cannot now alter what is inside, since, in the storyline of this paradox, the predictor has already done so with knowledge of your future action. The core dilemma is reflected in two logical stands. On one hand, there is the one-box strategy, choosing only box A in the belief that the predictor has foreseen this choice and so has placed the million inside. This leads you to obtain the million, leaving the 1,000 aside, but you gain far more if indeed the predictor stashed the big prize there. On the other hand, we have the two-box strategy. Since box B clearly has 1,000 guaranteed and box A's contents are already decided, one might see it as irrational to forego a sure 1,000 because that content will not change post-choice. From a purely causal viewpoint, by the time you choose, Box A either has the million or it does not, unaffected by your subsequent action, so it appears more logical to grab both. This is known as causal reasoning, concluding that you should always take both, as you cannot undo the past. In contrast, the one-box strategy, often called evidential reasoning, says that picking only box A provides evidence that the predictor will have anticipated exactly that, so box A likely holds the million. Should you take both, your own decision reveals that the predictor would have inferred it and thus placed nothing in box A. Therefore, if you want to maximize your payoff, it is better to pick only box A, because that is normally how people in this paradox come away with the million. Of course, this standpoint implies that taking or not taking the second box retroactively affects the probability that box A has the million, clashing with conventional time-based causality. The paradox can be summarized as follows. Argument favoring taking both boxes. What's in box A was determined before I walked in. Whether there's a million in there does not hinge on what I do now. Therefore, it's foolish to miss out on the 1,000 in box B. Given that the content in A will not magically change, it's rational to take both. Argument favoring taking only box A. If the predictor is near infallible, then my taking only box A suggests it foresaw that choice, so it likely put in the million. If I take both boxes, I reveal I was predicted to do so, and therefore box A is empty. To make the bigger gain, I must trust the predictor's accuracy and just pick the opaque box. Practically, advocates of standard game theory typically fall under the causal trap. Once you arrive, the million is either there or not, so you always pick both boxes. But the Bayesian or evidential stance claims that your actual action reflects the type of person you are, and the predictor has matched its choice to that. If you take both, it means the predictor likely foresaw that, so no million in A. If you pick only A, it indicates the predictor likely concluded you would, and so the million is presumably inside. In polls, people divide. Some pick only A, others pick both, and the debate can become heated. The puzzle's allure lies in that it is not just a logic paradox of self-reference like this sentence is false, but a scenario in decision theory that merges causality and evidence-based reasoning. If you believe strongly in linear causality, you lean toward two boxes. If you emphasize the notion that your current decision is evidence about what the predictor deduced, you choose one box. Strictly speaking, there is no unanimous consensus on which is the perfectly rational choice, and the paradox exposes the clash between so-called evidential decision theory and causal decision theory. Some analogies appear, such as a predictor that knows your character. If it knows you are greedy and will always want both resources, it won't leave a large prize in the dark. But if it infers you have the determination to pick only one box, it will place the million there as a reward. When you finally decide, the temptation to pick both is ever present, but doing so presumably confirms the scheme that leaves you without the big reward. The controversy faintly echoes the prisoner's dilemma by questioning whether the immediate quest for maximum short-term gain or preserving logical consistency is best. Formal analyses of Newcomb's paradox often revolve around a scenario where the probability that the million is inside box A depends on the probability that you will pick one box or both. Under certain assumptions, the single-box approach carries a higher expected value if the predictor's accuracy is high enough. Yet if you adopt the logic that the predictor's choice has already been made, picking both boxes is validated from a purely causal viewpoint. Crucially, unlike more mathematical paradoxes, Newcomb's paradox places you in the role of a practical agent, not just recognizing a contradiction, but deciding how to maximize your gains. And that choice seemingly exerts a retroactive influence on what was decided beforehand, thanks to the near-perfect predictive power. It's essentially a discussion about free will, predetermined actions, and Bayesian correlation. It has been compared to whether it's worthwhile to pray for something that has already happened, or whether it makes sense to regret a misdeed that cannot be undone, with the hope of having altered the past. Although not exactly the same situation, both illusions revolve around a mismatch in intuition. Praying does not alter the past event, just as picking only A does not alter the content. However, the paradox states that if you trust in the predictor's skill, your present choice and the prior setup are not independent. The ongoing argument over whether one box or two boxes is the correct solution remains lively in philosophy. Those backing one box usually side with evidential decision theory, holding that there is correlation between how you act and how the predictor stocked box A. Those favoring two boxes uphold causal decision theory, which asserts that at the point of choosing, nothing can change what's already in the box, making it logical to grab both. In any event, Newcomb's paradox is valuable for challenging the notion that utility maximization is obvious. It teaches the difference between causation and correlation, and how the knowledge that an almost omniscient agent can forecast your actions impacts the scenario from the start. It also forces us to see how our convictions about how to act might shape the outcome before we physically make that move. Moreover, the paradox, like other game theory or decision puzzles, is not limited to a hypothetical game, but sheds light on real problems concerning anticipation, reputation, and the consistency of an agent in shaping strategic interactions. While rarely expressed so purely in daily life, politics, business, and social contexts do present parallels where some actors' predictive reputation heavily influences how others behave. Ultimately, Newcomb's paradox remains a point of contention among philosophers and economists, reflecting the tension between the causal viewpoint, once the box is set, it is best to pick both, and the evidential or functional viewpoint. If the predictor is accurate, it is better to pick only the opaque box, and thus get the million. There is no universally accepted resolution, which underscores how profoundly these logical collisions cut into human rationality. Even though it is a thought experiment, it continues to spark arguments about the essence of rational choice, temporal coherence, near-omniscient foreknowledge, and the ways in which our own decisions can effectively shape what was done in advance. Pascal's wager. In the history of philosophy and theology, few arguments have generated as much debate and at the same time presented such a simple premise as what is commonly known as Pascal's wager. Formulated by Blaise Pascal in the 17th century and included in his posthumous work, The Pensées, this proposal is not intended as a definitive proof of God's existence. Rather, it is a practical invitation to take the side of belief on the basis of a rational calculation of potential gains and losses. Over the centuries, it has given rise to a wide-ranging discussion involving everything from decision theory to more pastoral considerations about the sincerity of faith and the stance of agnosticism. The central idea can be summarized in a straightforward manner. In a state of uncertainty, where we cannot conclusively prove or disprove the existence of God, it is rational to place our bet in favor of belief, because the earthly costs of believing would not outweigh the potential benefits if, in the end, God truly exists. Despite numerous criticisms and caveats, Pascal's wager still stands as an intellectual exercise that sheds light on the tension between what reason cannot clarify and what the will might decide in its stead. The concise version of the wager states, "If God exists and you believe in him, you gain an infinite reward," which Pascal understands as eternal salvation or eternal bliss, whereas if God exists and you do not believe, you risk losing it all in spiritual terms, possibly facing punishment. Conversely, if God does not exist and you believe, your loss is finite time spent in religious devotion, sacrifices, moral restrictions, while if God does not exist and you do not believe, you do not gain a transcendent reward either. The core point is that even if the probability that God exists is very small, once you multiply that non-zero probability by the hypothetical infinite benefit or infinite loss, the expected value of belief exceeds that of disbelief. Consequently, if a person is in an agnostic position, lacking definitive proof either for or against God, the rational strategy is to bet on faith. The approach, viewed through decision theory, posits that an event of probability P, which offers an infinite reward, outweighs the probability 1p of gaining nothing, as long as p is not exactly zero. In Pascal's understanding, though the probability of God's existence might be tiny, the infinite nature of the possible outcome overshadows any smallness of that probability, so from a utility standpoint, belief is preferable. It does not attempt to prove God's existence. It only suggests that, from a perspective of maximizing expected utility, believing is superior to not believing. Yet, although this argument can be appealing to those uncertain about God, it has been challenged from multiple fronts. One of the oldest objections targets the nature of faith. Religion is not purely a matter of rational, calculative self-interest, but rather involves a deep conviction, grace, or personal experience. If someone feigns belief purely to attain the infinite reward, does that constitute genuine faith? Would an omniscient God reward an act of mere convenience? Some argue that the wager neglects the existential dimension of faith, going far beyond a purely pragmatic decision. Another key criticism is the so-called many gods problem. Pascal's wager is set within a Christian Catholic framework, presupposing that the choice is the Christian God or no God. But what if upon death it turns out a different divinity is real, one who might punish specifically those who believed in the Christian God? Under that scenario, Pascal's wager loses any unique force. It does not indicate how to pick among potentially countless deities, all offering infinite boons or dooms. Thus, it fails to address how to discriminate among the various religions that promise similarly infinite outcomes. Moreover, it is sometimes contested whether the probability of God's existence is truly non-zero. Certain individuals might consider that probability so minuscule, or effectively zero, that it would not be worth wagering on. Of course, Pascal counted on an honest agnostic being willing to grant a probability above zero to God's existence, however small. Also, not everyone accepts that the reward is infinite or that punishment is infinite, since theological viewpoints may vary from classical Christian orthodoxy. If no such duality of eternal bliss or eternal loss exists, the calculus shifts significantly. Another crucial factor is the actual cost of believing. Pascal tended to understate it, suggesting that if God does not exist, the believer only loses a finite amount of time or some minor earthly pleasures. Yet religion can involve far more substantial sacrifices, moral constraints, possible external persecution, conflicts with science or everyday freedoms. Some might see such costs as quite significant. Nor is it guaranteed that a devout life is entirely benign on earth. A person might endure hardships for following certain religious commitments. From that angle, it is not so obvious that the loss is trifling if God does not exist. Nonetheless, what has preserved Pascal's wager in philosophical debate is how it merges decision theory under uncertainty with theological reflection. Pascal recognized that pure reason alone might not conclusively settle God's existence, so willful engagement, guided by potential utility, could fill that void. If one grants even a small chance of divine reality, the possibility of eternal salvation outweighs any worldly sacrifice. In that sense, the argument moves the conversation from theoretical demonstration to practical conduct. If you cannot prove it, what is your best move, given the stakes? Subsequent philosophical discourse has not taken Pascal's wager as a definitive demonstration of anything, but has employed it to show that, in scenarios involving infinite or absolute stakes, rational decision-making may run contrary to everyday intuition. It can be considered an illustration of how merely positing a non-zero probability of an infinite reward or punishment can push an apparently logical decision into a realm that defies normal experience. Indeed, it serves as a lesson about the difficulties humans face in mixing probability with infinite or absolute values. Historically, it's revealing that, besides his scientific brilliance, Pascal was deeply religious, linked to the Catholic Jansenist movement. His intention was not merely an intellectual ploy, but a pastoral attempt to persuade skeptics to engage with religion. He posited that if someone, in the absence of certainties, began behaving as though God exists, praying, receiving sacraments, adopting moral discipline, perhaps that practice would bring authentic faith in due course. This underscores the fact that the wager is not purely a piece of decision theory, but also a tool of spiritual persuasion, reflecting Pascal's personal convictions. In modern times, critics have refined their challenges. One might consider multiple gods or religions, each offering or threatening infinite outcomes. One might note that the real burdens of belief are not trivial, or one might focus on how minuscule the probability assigned to a specific god could be. Still, Pascal's original text remains an instructive example in teaching how any scenario involving an infinite payoff and a non-zero chance can destabilize standard rational calculations, regardless of how unconvincing it may be on theological or moral grounds. Thus, Pascal's wager stands neither as a rigorous logical proof nor as an unassailable argument. It is better described as a practical invitation, which, notwithstanding the many counter-arguments, exerts considerable influence on how we discuss faith and rationality. It exemplifies how reason might shift from theoretical demonstration to pragmatic counsel in the face of an elusive question like God's existence. By underscoring that risking finite earthly resources might be outweighed by infinite celestial gain, Pascal's wager has guaranteed itself a permanent place in philosophical and theological debate. For some, it is a starting point for reflection on the sincerity of faith, the cosmic scale of potential rewards or punishments, and the puzzle of multiple religions. For others, it is questionable because it leads to fake belief or overlooks the variety of actual religious doctrines. Even so, it remains a notable device to consider how the human mind grapples with incomplete evidence, large potential consequences, and the tension between reason's limitations and the will's capacity to act. In some sense, it reflects Pascal's ingenuity in translating the mystery of salvation into the language of mathematical calculation, revealing that, at times, practical reason could nudge individuals where pure theoretical reason falls short. Galileo's paradox. In the history of understanding infinite sets, what is known as Galileo's paradox holds a prominent position as one of the earliest observations to unsettle the traditional view of quantity. It is attributed to a reflection by Galileo Galilei, who noted something that, in his day, seemed startling. Even though square numbers appear to constitute a strictly smaller portion of the natural numbers, the two groups, when examined through a certain matching, end up having the same infinite size. This discovery intrigued his contemporaries, for it appeared to contradict the notion that the whole is greater than any of its parts. The classic formulation is outlined as follows. Suppose we look at two sets of numbers. On the one hand, we have the set of all natural numbers, 1, 2, 3, 4, continuing indefinitely. On the other hand, we have the set of perfect squares, 1, 4, 9, 16, 25, and so forth. Clearly, every square number is also a natural number, while most natural numbers are not squares. At first glance, one might think there are more natural numbers than perfect squares. For instance, among the first 100 integers, only a few are squares, and as the list grows, the fraction of squares keeps decreasing. Yet if we define a function that assigns to each natural number n its square, maps to min times nin, we obtain a one-to-one correspondence between natural numbers and squares. Each natural number has a unique square, and each square corresponds to exactly one natural number. Therefore, from the perspective of infinite sets, the two sets, despite one being a proper subset of the other, share the same cardinality. During Galileo's time in the 17th century, the formal set theory that would emerge later with the concept of cardinality did not yet exist. Galileo simply pointed out the apparent contradiction. On one hand, squares seem fewer. On the other, the function that sends each natural number nin to nin squared suggests they possess the same infinite quantity. He concluded that the rule, if something is a proper subset, it must be smaller, fails when dealing with infinite sets. This foreshadowed what modern set theory, especially with Georg Cantor, would eventually formalize. A set is infinite partly because it can be put in a one-to-one correspondence with some proper subset of itself. Before Cantor's era, the infinite was perceived as a paradoxical concept tied to ideas such as Zeno's or theological speculation. Galileo realized that, in the case of squared numbers, the usual thinking inherited from finite experience that the part is strictly smaller than the whole breaks down. For a finite set, removing some elements means there are fewer left, but for an infinite set, a portion can be the same size as the entire set, in the sense that a bijection can be established. The paradox arises when we try to apply finite principles of comparison to something infinite. The content of Galileo's paradox is employed today as a teaching tool to illustrate this principle. There exist proper subsets of an infinite set that, even though they appear smaller, have the same cardinality. In modern terms, cardinality is the notion that defines whether there is a one-to-one pairing between two sets. With the naturals and the squares, the function that associates an n with nn times an nn is precisely such a pairing. As a result, the paradox ceases to be an unsolvable puzzle and becomes an early example of the concept of cardinality that Cantor would define rigorously in the 19th century. It is worth noting that, in his day, Galileo did not solve the issue with a set theoretic approach. He merely drew attention to it and concluded that our usual rules of bigger or smaller fail for infinity. In the mind of that era, this was significant evidence of how the infinite had exceptional traits that defied everyday reasoning. It required Cantor's efforts to consolidate the notion that two infinite sets share the same cardinality if there is a one-to-one matching, such as that between naturals and squares. Cantor's formalism demonstrated that integers, even numbers and squares, all have the same cardinality called countably infinite. The impact of the paradox becomes more apparent if one thinks, if we list 100 natural numbers, only a handful are squares. If we list 1,000,000, the proportion of squares is even smaller. Why, at infinity, do they match up? The reason is that in the infinite realm, the density of a subset can decrease to almost nothing without implying that the subset has fewer elements in terms of cardinality. This phenomenon clarifies the distinction between density and cardinality when we talk about infinite sets. The proportion of squares among naturals shrinks as the sample grows, but the cardinalities coincide because a one-to-one map can be made without leaving out any member of either set. There has been historical inquiry into how fully Galileo grasped the scope of this observation, or whether he was simply highlighting a puzzling feature that indicated finite-based logic breaks down with the infinite. In any case, his commentary paved the way for later reflections, setting the scene for the methodology that centuries afterward would show that the part versus whole argument does not measure up in the infinite setting. In modern instruction, Galileo's paradox is used to show that, for example, the set of even numbers is also in bijection with all naturals, or that the positive and negative integers combined also match the naturals in size. Those unaccustomed to set theory often protest. How can it be the same when a subset is missing so many elements? That is precisely the conceptual jolt the paradox highlights. A proper infinite subset, which in finite logic is obviously smaller, can have the same cardinality as the entire infinite set. Some call this experience the first step toward the arithmetic of the infinite, because it demands recognizing that the notion of fewer elements cannot rely simply on being a proper subset, as happens in finite sets. Galileo's example with squares provided a powerful instance. Each number n is linked to its square, n multiplied by itself, and although it might appear that we are picking out very few, the cardinal reality of the infinite is more subtle. This phenomenon also enriches discussions that include the continuum hypothesis and other advanced questions. It shows how, in various infinite cases, parts can be as large as the whole. But Galileo's paradox is confined to illustrating the scenario in which both sets are countably infinite. For some, the paradox was an initial impetus toward the concept that the notion the whole must be bigger than every part is invalid in infinite contexts, which conflicts with our typical intuition. Many historians of mathematics note that although Galileo did not conclusively solve the puzzle under an axiomatic system, he left evidence that with infinite sets, we must reinterpret bigger, smaller, or equal. This awareness foreshadowed the revolutionary approach to the infinite that would flourish 2 centuries later under Cantor's transfinite arithmetic. Likely, Galileo did not set out to devise a full theory of cardinalities, but his keen observation let him spot in a rudimentary way the distinction that emerges once one moves beyond the finite. In modern times, Galileo's paradox is used to introduce the idea that an infinite set can contain infinitely many subsets sharing the same size as that entire set. One frequently cited example is that the set of even numbers and the set of all natural numbers are the same size in cardinality, or the set of all negative and positive integers is as large as the set of naturals, despite each set seeming like a subset of the others if considered in a finite sense. This retains a paradoxical flavor for those unacquainted with infinite logic. Galileo, with his squares example, offered one of the earliest recorded hints of that disconcerting property. People also discuss the historical context. Galileo was already at odds with various institutions over his astronomical theories, so when he examined the infinite, he approached the subject with caution. Although not a theologian, his openness to paradoxes of the infinite fitted his broader spirit of experimental inquiry. This merges the strictly mathematical dimension with his epoch's intellectual climate, which was tentatively pushing the boundaries of accepted knowledge. Practically speaking, Galileo's paradox served as a precursor to many others. For instance, Hilbert's infinite hotel descends conceptually from similar ideas. Both show how, in infinite realms, reconfigurations can defy common sense. Hilbert, for his part, describes a hotel with infinitely many rooms that can always admit more guests, even if it is full, which parallels the idea that an infinite subset can be rearranged to match the entire set, just as mapping nin to n plus 1 n plus 1 n plus 1. Galileo's case with the squares uses the same principle, demonstrating the alignment n maps to n times n. Both illustrate that the intuition about subtracting part of a finite set reduces its size does not carry over to the infinite. The controversies or discussions sparked by Galileo's paradox were eventually answered by Cantor's systematic approach. Cantor introduced a hierarchy of infinities and showed that some infinite sets are indeed larger than others, for instance, real numbers surpassing the naturals. But for certain pairs of infinite sets, such as naturals and squares, or naturals and even numbers, there are bijections proving identical cardinality. Galileo thus heralded that concept without fully developing it. Even today, despite our advanced mathematics, Newcomers often confront Galileo's paradox with the same surprise it caused in the 17th century. It attests to how a mind, shaped by finite everyday experiences, can be startled by the unique properties of the infinite. It emphasizes the crucial role of formal definitions in handling such properties to avoid illusory contradictions. Galileo's paradox, therefore, occupies historical and educational significance in grasping the infinite. It demonstrates that the notion of having more elements cannot be judged merely by the idea that one set is a proper subset when confronted by the infinite. The realization that the mapping n goes to n times n pairs each natural with a square, coupled with the observation that squares appear only sporadically in the overall numbers, creates this twofold paradoxical view. Interpreted in modern language, it says that the squares, being a proper but infinite subset, have the same size as the larger set, contradicting the instincts derived from finite numbers. Many observers of mathematics emphasize how Galileo did not resolve the paradox formally, but recognized that, regarding the infinite, the usual comparisons are not valid. This step was an anticipatory clue of what would become the profound, structural rethinking of the infinite in set theory. He was not aiming to produce a comprehensive theory of infinite cardinalities, but his acute eye led him to perceive a phenomenon that stands apart from ordinary, finite logic. In current times, the paradox is used to demonstrate that, when dealing with an infinite set, the part can match the size of the whole. The example with squares is especially straightforward, yet potent. Every n is associated with n times n, so although squares seem so few, the cardinal arithmetic of infinity tells a more subtle story. This same reasoning clarifies various deeper investigations of the continuum and higher mathematics, which confirm that in the domain of the infinite, standard assumptions about subsets can fail dramatically. Galileo's case is confined to showing that both sets in question are countably infinite, but the philosophical lesson is still that the whole need not be bigger than the part for infinite sets, contrary to finite habits of mind. Those who see it from a historical perspective appreciate how, before Cantor's formal definition of infinite sets, Galileo already hinted at the notion that infinite totalities behave under different rules. His remark, in effect, introduced a minor tremor into the comfortable tradition that had insisted the entire set must have strictly more elements. Over the next 2 centuries, Cantor would turn that tremor into a formal revolution by unveiling transfinite arithmetic. Within educational contexts, Galileo's paradox shows up as a natural stepping stone for novices to see how sets like the squares and the naturals, or the even integers and the naturals, can have an equal number of elements from a cardinal standpoint. This instructive contrast between fewer in every finite sample and matching in an infinite sense resonates with learners because it remains so counterintuitive. Galileo, by singling out squares as a notably sparse subset, highlighted an early example of how infinite sets defy the naive principle that the subset is smaller than its superset. All of this is why Galileo's paradox stands as a lasting demonstration that infinity has properties that clash with finite-based expectations. That recognition paved the road for a new understanding of counting in the infinite domain, ultimately culminating in Cantor's revelations. The paradox continues to prompt reflection not only on how mathematics approaches infinite sets, but also on how the human mind grapples with comparisons that become unmoored once the numbers extend beyond any finite threshold. The Abilene Paradox. In organizational psychology and group decision-making theory, what is called the Abilene Paradox highlights a highly curious phenomenon. A group of people, out of fear of dissent or due to mistaken assumptions about everyone else's preferences, ends up carrying out a collective decision that none of its members actually wanted. This paradox, introduced by management consultant Jerry B. Harvey in the 1970s, is illustrated by the story of a family making an uncomfortable and pointless trip to the city of Abilene entirely because each person believes the others truly wish to go. The specific anecdote demonstrates how a lack of genuine communication and the desire to avoid conflict can lead a group to do something collectively that no one individually supports. The typical anecdote depicts a group of people on a scorching summer day in Texas. While relaxing on a porch, someone suggests taking a car trip to Abilene, a place far away with even more sweltering weather. The rest of the group, without showing genuine enthusiasm, agrees to the trip because each person thinks the others want to go. In truth, all feel somewhat reluctant, yet assume that the collective preference is in favor of heading off. Ultimately, after enduring a tiring, joyless excursion, they discover that none of them truly wanted to go in the first place. The group nonetheless undertook the adventure purely to comply with what each one believed was everybody else's desire. The Abilene Paradox exemplifies a misstep in group communication, whereby each member fails to voice their real concerns, believing they are alone in disagreeing. This silence fosters the illusion of unanimity, and the final decision ends up fulfilling a collective preference that does not exist. The story becomes emblematic of how an organization or a team might adopt a course of action that no one individually favors. Typically, this arises when the group confronts a proposal or problem, and each person, in order to avoid confrontation or disturbing harmony, keeps their objections to themselves. The situation worsens if others, seeing this apparent acceptance, also refrain from questioning in order not to stand out. The resulting action typifies the paradox. Everyone does something that nobody wants. A key aspect is the mistaken interpretation of signals of conformity. In many group decisions, there is a tendency to think, if no one objects, it must be acceptable to them. No one dares to reveal any disagreement for fear of sparking conflict or undermining supposed harmony, and this passivity reinforces the illusion that all are in agreement. The phenomenon can be linked to a well-known concept, group polarization, although the Abilene Paradox focuses more on the group's undertaking something that no single member actually desires, while group polarization typically involves adopting more extreme positions that group members do, in fact, share to some degree. The anecdote was created by Jerry B. Harvey to demonstrate how organizations, families, or work teams can end up launching harmful or pointless initiatives because of incorrect assumptions about unanimous support, plus inadequate communication and fear of internal disapproval. Consequences can manifest as failed projects or decisions at odds with the real interests of the group. Beyond the anecdote itself, it underscores the need for transparent communication and for encouraging constructive disagreement. If a leader or member of the group dares to say, "I am not comfortable with this idea," the spell is broken, revealing that such a feeling is not unique to one person. In addition, it differs from the so-called spiral of silence, which describes how people might stay silent about minority opinions for fear of negative reaction by a majority. Under the Abilene Paradox, the situation is not merely that someone refrains from expressing a minority view, but that they wrongly believe there is a consensus in an opposite direction. This misunderstanding is collective. Each individual holds back from challenging what they assume others favor. Summarized in simpler terms, the group is motivated by everyone acts to please each other, but nobody actually desires the outcome, creating a self-sustaining loop of apparent conformity. The effect commonly arises in contexts where group cohesion or respect for authority is significant, as well as in organizational cultures that discourage open criticism or disagreement. People, not wanting to cause discomfort, feel that staying silent is best. However, such passivity is interpreted as consent, which in turn reinforces the decision. The attitude, "I would rather go along than cause trouble," culminates in a scenario that obliges the group to select something no one wanted. Often the paradox only becomes evident after the decision is carried out, when participants admit their discontent and realize they all actually preferred a different course. The name stems from the fictional location of Abilene, the city that the family in the story travels to with no genuine eagerness to go. The episode is so illustrative that many have adopted Abilene as a metaphor for any trip or undertaking that a group chooses, even though no one truly desires it. A typical real-life case might be a work committee approving a complicated, costly plan destined for failure, only to discover afterward that each member was dubious, yet believed everyone else favored it wholeheartedly, and thus did not voice objections. The result could have been different if at least one person had voiced doubts, giving others the confidence to express their own skepticism. Under the paradox's influence, the group moves forward, driven by this illusory group preference. Hence, the Abilene Paradox underscores how crucial it is for a team to maintain an atmosphere that allows someone to say openly, "I do not agree," "This is not a good idea," or "I prefer we not do this." Such candor can prevent unnecessary detours, cost overruns, and widespread dissatisfaction after the fact. Some authors suggest methodologies in management that incorporate the role of devil's advocate or explicitly invite dissenting opinions, ensuring that each individual understands that voicing disagreement is recognized as beneficial, not as undermining group unity. In that manner, the group is protected from the false unanimity, leading to an Abilene-like result. It is also essential to differentiate the Abilene Paradox from the mere imposition of a dominant leader. While sometimes subordinates may comply with a superior's directive without question, the essence of the Abilene Paradox is that there is no overt command forcing the group. Instead, there is a collective misunderstanding. Each person believes the others want this, and thus remains silent or consents out of caution. The paradox is all the more striking because there is no external compulsion that leads to the outcome, but rather an internal belief that the rest are in favor. Connected to that is the desire not to disrupt group harmony. People frequently want meetings to avoid overt confrontation, and in preserving superficial harmony, nobody dares to voice dissent. However, that superficial harmony often spawns a decision that, paradoxically, generates even greater collective frustration. Discontent emerges openly when, after implementing the plan, everyone admits, "I never actually wanted to do this," and discovers that others felt the same. This revelation reflects the paradoxical nature. The group adopted an unwanted course, driven by the illusion of unanimous support, when the real majority was in fact opposed. Various studies in social psychology and behavioral sciences have revisited the Abilene Paradox to examine the extent to which flawed communication, aversion to conflict, and the pursuit of positive regard can produce these outcomes. It is not confined to families. Numerous instances occur in business organizations, companies, academic institutions, or governments, in which an initiative that everyone privately considers doomed still goes forward. The universal factor is collective silence fostering the mirage of consensus. Ultimately, the Abilene Paradox exhibits how a group may act upon something that nobody truly wants. It cautions both individuals and leaders not to rely automatically on the absence of objections as a sign of genuine agreement. The remedy is to encourage open inquiry. Does anyone have concerns? Where critique is not penalized, and where presenting a differing view is welcomed as a legitimate step in decision-making. Only thus can we avoid mobilizing everyone toward an uncomfortable journey to Abilene, that symbolic place no one honestly planned on visiting, but which they ended up traveling to purely for failing to express their true preferences and objections. Simpson's Paradox. Within the field of statistical data analysis, what is referred to as Simpson's paradox stands out as one of the most intriguing yet illustrative phenomena. It describes a situation in which a trend observed in various subgroups of a population can vanish or even reverse when those subgroups are combined into a single overall set. Consequently, something that appears to point in a certain direction within each separate part can yield the opposite direction once all the data are aggregated. This apparent reversal has been documented in fields as diverse as medicine, economics, sociology, psychology, education, and more. At first glance, it seems paradoxical because a reasonable assumption is that if a pattern is clear in each subgroup, one would expect to see that same pattern or a reinforced version of it in the overall total. However, Simpson's paradox defies that expectation when there is a third variable or multiple variables distributed differently across the subgroups, capable of completely inverting the correlation or trend of interest. The name Simpson's paradox comes from the statistician Edward Hugh Simpson, who described such a statistical reversal in the 1950s. Even so, similar examples had been noted previously by other authors, and it forms part of a set of observations emphasizing that, when dealing with averages or proportions, how data are grouped or combined can dramatically alter the conclusions. Much of the surprise arises because common sense tells us that a pattern found in each separate subset should be visible in the combined data as well. The paradox calls that notion into question by revealing the strong influence of stratification factors and possible confounding variables. One of the most famous examples used to illustrate Simpson's paradox concerns admissions at the University of California, Berkeley in the 1970s. Examining overall acceptance rates for men and women, it initially seemed that women had a lower admission rate than men, suggesting possible gender discrimination. But when looking at the data disaggregated by department, one could see that in most cases, the acceptance rate for women was equal to or even higher than for men. The apparent contradiction arose because women were applying disproportionately to certain highly competitive departments that admitted relatively fewer applicants, while men tended to apply to departments with higher acceptance rates. When all applicants were combined without considering department differences, the overall proportion of female acceptances looked lower, which masked the lack of bias within most individual departments. Hence, ignoring that department was a key factor led to the paradoxical inversion from what the subgroups had shown. This example underscores that an in-depth understanding of how variables are distributed is crucial for avoiding misleading conclusions. Simpson's paradox can be illustrated through a simpler, hypothetical scenario. Imagine two medical treatments for an illness called Treatment A and Treatment B, and the patients are split into two groups according to disease severity, mild and severe. Observing the data, one might find that for the mild group, Treatment A has a higher success rate than Treatment B. Similarly, for the severe group, Treatment A also shows better results. However, when those groups are merged into a single whole, it could turn out that the overall success rate with Treatment B is higher than that of Treatment A. In other words, A appears superior within each subgroup, yet B emerges as superior overall. Usually, this outcome is due to the fact that the patients under Treatment A may consist largely of severely ill individuals who typically have a lower success rate, while B is applied more often to mild cases. Taken in aggregate, B seems to outperform A, even though in every specific stratum A was more effective. Such statistical reversals do not imply any error in the data. Instead, they convey a methodological lesson. The correlation or advantage seen in the aggregated set can diverge from what is observed in each subset. From a probability and statistical perspective, one concludes that the variable defining those subgroups, for instance department, disease severity, region, and so forth, often correlates with both the explanatory variable, treatment, gender, or whichever, and the outcome variable. success, acceptance rate, etc. This correlation can distort the direct comparison if that third variable is not properly accounted for. The paradox exemplifies that trusting solely in combined data or overall averages can lead to conclusions that might be inconsistent when considering subgroups individually. This phenomenon also strongly emphasizes the difference between correlation and causation. If one merely looks at the total correlation, one might draw the conclusion that treatment B is better than treatment A, or men are admitted more frequently than women, or some product is more successful, but fail to realize that a confounding variable's uneven distribution drastically alters the apparent direction of the relationship once it is disaggregated by subpopulations. In practice, this is why many scientific and medical studies stress stratified or multivariable analysis. Methods like regression are often used to adjust for additional variables and isolate the specific effect. Simpson's paradox acts as a warning about how combining data without proper adjustments or stratifications can yield a complete flip in interpretation. Equally relevant is how Simpson's paradox affects the way data are presented to non-technical audiences. Often the media or institutional reports show only overall totals, omitting the breakdown that might show a different story. For example, a headline might state, "Mortality is lower with treatment A than B," neglecting to mention that the group given A was younger on average or in a better prognostic bracket, thus distorting the comprehensive comparison. This demonstrates that clarity in data segmentation is essential so as not to be misled by illusions caused by aggregated statistics. The paradox thus becomes evidence of the importance of thoroughness and honesty in publicizing results. A common moral of Simpson's paradox is that the combination of data from distinct sources or subpopulations can deceive, not only with separate statistical subgroups, but also with data from different time periods or from regions that vary in demographics or data collection methodology. If someone lumps two data sets together without accounting for their disparities, it might create the paradox. The old adage, "Do not mix apples with oranges," takes on a formal statistical meaning here. It encourages an approach that is systematic and mindful of the underlying structure of data. A fundamental lesson from this paradox is that data analysis requires careful segmentation. That is, big picture summaries may contradict the findings in each partial group. Whenever a pattern seems straightforward, it is helpful to ask, does that trend remain the same upon subdividing the sample according to relevant variables? How does it look in smaller, more homogeneous groups? If the direction of the pattern changes dramatically, that is likely the hallmark of the paradox and points to the factor that triggers it. Sometimes it is said that the paradox is no real paradox from a mathematical standpoint, but it is indeed surprising to many people precisely because aggregated data can differ so strongly from the separate group data. This property has an enormous pedagogical value. Once a student or researcher sees an example of the pattern in each subgroup is reversed in the total, they rarely forget how easily misinterpretations can arise. It reveals the traps of doing a single global analysis or average without considering the distribution of subgroups. Through that lens, Simpson's paradox is intimately related to the necessity of including third variables in data interpretation. For instance, if globally X is associated with Y, but in each subgroup X is inversely related to Y, it might be that the variable that defines the subgroups is confounding the overall correlation. A well-known case, one treatment is better in each stage of an illness, but is worse in the combined total. Or, one gender sees a higher acceptance rate in each department, yet in the entire university data, it looks the opposite. In all these situations, the subgroups differ in some key aspect, such that the proportion of data points in each group modifies how the global average plays out. This phenomenon also arises, for instance, in clinical trials. If one merges data from different hospitals or different patient risk categories, one might incorrectly judge one drug as superior or inferior. For that reason, advanced statistical methods were developed to identify such confounding. The paradox underscores once again that it is not enough to gather data properly. Interpreting them correctly is equally vital. It can even inform real-life decisions, where an entire population's big number might contradict local or subgroup outcomes. An added complication is the dimension of time. One can see reversed patterns if data from different eras are pooled incorrectly. Perhaps in the first few months, a variable shows upward movement for Group A, and in the next few months, similarly upward for Group A. But once the entire time span is aggregated, Group B might surpass Group A overall. The reason can be that the volume or the conditions in each period were different for the two groups, so the aggregated perspective yields an opposite conclusion. This extension parallels the standard scenario in which the subpopulations are different categories, but time acts as the stratifying variable. Simpson's paradox is often characterized as a demonstration that a partial view of the data can be more representative of reality than the aggregated view, turning the typical assumption on its head. This is not to say that a global overview is always worthless. It simply means that potential confounding or distribution differences can produce illusions. Indeed, an essential best practice is to do both a global check and a stratified or adjusted check, ensuring that the observed global pattern is robust across relevant subgroups. If a discrepancy arises, it is important to investigate possible confounders. Its name, paradox, arises mainly from the shock or confusion it causes when first encountered, because it subverts the everyday idea that if all parts show the same sign or direction, then combined they must do the same. Statistically, it is not contradictory. The mathematics behind it reflect that the third variable, often controlling how data are distributed, can overshadow the direct association. Nonetheless, the impact on novices is profound. How can each piece point one way, yet the total set points the opposite? In conclusion, while it may not be a paradox in the strict sense, Simpson's paradox stands as an enduring lesson. Data must be scrutinized by subgroups or controlling for potential confounders to avoid misinterpretation. Everyone from statisticians, epidemiologists, to social scientists who handle data frequently must be aware that an aggregated correlation or difference might invert once the distribution among subpopulations is clarified. That principle is crucial in presenting and interpreting data responsibly. The result is a deeper appreciation for the complexity of relationships among variables, the significance of adjusting for confounders, and the diligence needed in not drawing hasty conclusions from a single overall statistic.